Well, students, today we get notes for section 1.2. 1.2, titled Classification of Matter. In this, very basic ways to classify matter. Some of the terms we'll be looking at: pure substances, mixtures, elements, compounds. So matter can be classified by state, solid, liquids, or gas, or by composition, an element, compound, or mixture. We'll look a little at each of these. States of matter, when we're dealing in chemistry, and we just look at solids, liquids, and gases. There are other states of matter that we don't typically use in chemistry, such as a plasma. Plasma relates to the stars, the fluorescent lights, to fire. In chemistry, we generally just classify solid, liquids, and gases. And then we have some very basic properties looking at the macroscopic level, why solids, liquids, gases are as they are. Gases, no fixed volume or shape, conforms to the shape of the container, it's compressible. Liquids, volume is independent of the container, meaning it has a fixed volume, it's not going to change. We consider it to be incompressible. It has no fixed shape, it takes the shape of its container. A gas, besides taking the shape of a container, will always fill its container. And then a solid, both its volume and shape are independent of its container, means it has a fixed volume and a fixed shape. It's tend to be rigid and incompressible. So this is at the macroscopic level, the things we can see. Now, we look at the molecular level, or the sub-microscopic level. We see why these things happen. Gases take the shape of their container, they're compressible, all these things because their molecules are far apart, they move at high speeds, they collide often. So the molecules are moving around a lot. It would be like put a bunch of people in a gymnasium and just all start running around, banging into each other. Go as fast as they can until they hit something. Now, liquids, molecules are closer together than a gas, usually very close together. They move rapidly, but they always stay close together and slide past each other. It'd be like if you're moving down a crowded hallway. You can move through, you can move around, but you're always going to be close to somebody. And in solids, the molecules are packed closely in definite arrangements. Why? They're rigid. They don't move around much. They just kind of sit there in the same spot and vibrate a little bit. Here we have a diagram from the book where they ask you a simple little question: which form of water are the molecules farther apart? Hopefully that's not too difficult to figure out that that's a gas. Yeah. Been using, we got the term gas and vapor. A vapor is something that is normally a solid or liquid at room temperature. So vapor is a gas, but a vapor is always a gas, but a gas doesn't have to be a vapor. So we'd say, like here, they use the term water vapor. We would never say oxygen vapor, because oxygen's always a gas at room temperature, where water is a liquid at room temperature. So if we have it as a gas, we call it a vapor. And they give you some nice little sketches of how things are. Again, in the vapor, gas, molecules are far apart, don't really show the movement here. Liquid close together but rearranged or random order, and the solid still close together but in much orderly arrangement. And we look a little bit at what we term pure substances. Pure substances, fixed composition, and distinct proportion. Pure substances are either an element or a compound. Elements cannot be decomposed into simpler substances, have only one kind of atom, but compounds consist of two or more elements chemically attached together. And if a substance or if matter is not a substance or a pure substance, with pure substance we often just say substance. Pure substance, substance, we're talking the same thing. So matter can be either a substance or a mixture. In a mixture, combination of two or more pure substances where each retains its own identity. The structure of the substances is not changed. Then we'll look a brief bit at elements. Here it says 116, but today we got 118 metal. That changes over time. As new elements are discovered or synthesized. They vary in abundance. I mean, some very little abundance. Some of the synthetic elements, not much exists. Two things that have a lot of abundance. And each element given a unique name, abbreviated by a chemical symbol. They're organized into the periodic table, and the symbols are one or two letters. You look at some periodic tables, you'll see some things that will have UU, M or something like that. Some three letters. These are temporary symbols. Currently, if you look at the most current periodic tables we don't have any of those on it, but as new elements are discovered, they're given one of these names until they're verified. And here is a chart with a few of the names and symbols, and many of them are very simple. I mentioned last video we're going to be memorizing names and symbols, things like carbon, really easy, C. And most of these match up nicely. Lithium, Li. As English is the language of science, so language of chemistry, so most things match up. We do get a few of them, these over here, that don't match up. You've got copper, comes from a word cuprum, a Latin word, iron, ferrum. Got a lot of different ones. Some of them that are good to know where they come from. Copper, because we do use that idea of cuprum. We'll talk about things like cupric chloride, or cuprous chloride. Iron, ferrum, tin, stannum, and lead, plumbum. So those four, it's good to know the Latin names, what we're talking about, and we'll, as we get into what we'll call some nomenclature later, we'll come back to that idea. But you need to memorize and say things such as copper is Cu, mercury is Hg. Then from our textbook, got this little chart I mentioned on the preceding slide, that we had different abundances, and this just gives abundance in the earth crust and in the human body. And you can see it can vary from what here, 7% of the human body is made up of all the other elements except for hydrogen, carbon, and oxygen. So 93% is those three elements. Where Earth's crust, you see, got a few more elements with decent amounts, but then you got everything else 9.2%. So quite a variance in the amount of these elements that are present in nature. And the question here, can you name two significant differences between the composition of Earth's crust and the elemental composition of the human body? And we should note that we have different elements. And we have different amounts. Such as in human body, oxygen is 65%, where in Earth's crust it's 49%. Look at hydrogen's 10% of the human body, but doesn't even appear in the top few for the Earth's crust. It would be among the others. Then we get to a little information on more on compounds. So compounds, combination of elements. So we got like H2O combination of H and O. And the opposite of compound formation is called decomposition. So you can form or synthesize compounds and decompose. Compounds have different properties than their component elements, such as water is liquid, hydrogen and oxygen, both gases at room temperature pressure. A number of other things that go along with that. You can see some of these other differences in this chart. One that's a little surprising is when they talk about flammability down here. Water's not flammable, hydrogen is, but it might surprise you that we consider oxygen to be non-flammable. It causes things to burn, but it does not burn itself. It needs to be there for other things to burn. And then we got a little bit about the law of definite proportions developed by a guy named Proust. And it just says that a compound always consists of the same combination of elements, such as water is always 11% hydrogen, 89% oxygen. Water is always H2O. Now, there is another thing called the law of multiple proportions that says these things can exist in other ways, such as it can be H2O2. So this is water, where this is hydrogen peroxide. You may have that at home in your medicine cabinet. I got another little thing from your book where it shows the electrolysis of water causes the water to decompose into its element, hydrogen and oxygen. And you note up here, and it states down here, volume of hydrogen is twice the volume of oxygen. So again, look here, you can see the hydrogen. This one is about twice as much as that one. So what's the connection between the relative gas volumes collected in the two tubes and the number of gas molecules in both? Volume and number of molecules you got twice as much hydrogen as you do the oxygen. That characteristic does not maintain itself for liquids and solids. But when we got gases, it does. And another question from your book. Hydrogen, oxygen, and water all composed of molecules. As we can see here, there's a water molecule. There's an oxygen molecule, and there's a hydrogen molecule. Now, oxygen hydrogens are things we call diatomic elements. Because they exist, these two atoms bond together. They don't exist in nature as what we see up here, not as atoms, but as molecules. So, their question then, and we'll have a few other diatomic molecules, and we'll catch that at a later date. So what makes water a molecule where these two are elements is because water has two types of atoms. So it's a compound where these two only have one type of atom. So each of them's an element. We'll get a brief little bit about mixtures, and we'll expand on this concept as we continue on. Mixtures, combination of two or more pure substances. And this we talk about as a physical combination, meaning they each retain their own identity. We talk about the components of the mixture. They can have variable composition, and we talk about heterogeneous mixtures and homogeneous mixtures. Heterogeneous mixtures do not have a uniform composition, properties of appearance, such as sand, or in the picture here, granite. Granite is heterogeneous. And many times with heterogeneous, you can just see different parts in there. Where homogeneous mixtures are uniform throughout, they are solutions. And this we call homogeneous mixture or a solution, a mixture of copper sulfate. Now we move to a little chart here just to summarize this information. So we start with matter. Matter can either be we'll break it down to heterogeneous or it's homogeneous. Heterogeneous will always be a mixture. That's based on, is it uniform throughout? Homogeneous then can be two things. It is uniform, does it have a variable composition, or if it does have a variable composition, and we call it the homogeneous mixture or solution. If it doesn't have a variable composition, that's its pure substance. And pure substance could be elements or compounds, depending on if it can be broken down or how many types of atoms they have. The last thing we get for this section, in your textbook they have sample exercises 1.1. They have the answers here. Sometimes I will talk about these, other times I don't, but you should always read them and make sure you understand them. So, in the first question, we got white gold. Contains gold and some white metals such as palladium. Some of the key things here, we're going to classify this. So the key idea is it's uniform. So because it's uniform, it's homogeneous, but they differ in the relative amount, so that means its composition differs, so that means it's not a compound, so it's a homogeneous mixture. You need to be able to take things like this and classify them as well. And then aspirin, made up of these percentages of different elements, and we want to classify aspirin. So it has a constant composition, and it can be separated in different types of elements, or it's made up of more than one type of atom, so that makes it a compound. So that completes section 1.2. Again, make sure you do the reading. Read section 1.2. Study it.